Greetings, everyone. What I'd like to talk to you about now is some relatively unknown pitfalls when you're using comparison, and particularly in comparisons with the utility algorithms in the standard library. So first of all, we need to understand what comparison is. As much as 50% of all instructions executed on a machine are on behalf of a comparison or the subsequent branches. So that's a lot. And an ill-formed or incorrect comparison can invalidate the entire program, which means that error rates of 1 in 10 trillion will cause a failure every day on every machine. So we need to pay attention to this issue. So even very rare events can come out and get us. But to carry on, we inevitably have to talk about a little math. So a comparison is a query against an equivalence or an order relation. So it's a mathematical operation, and there are mathematical properties associated with those. We'll start off with equality. What we have is an equivalence relation. Many operations provide a weak equivalence. It's reflexive, it's symmetric, and it's transitive. Most likely, if you're going to fail in delivering a weak equivalence, it's that you failed to deliver transitivity. And then the stronger thing, what we usually think of when we see operator equals, is that we give an equality or a congruence. It also adds the principle of substitutability. If A is equal to B, then every function on A will produce the same result as that same function on B. So it's a very strong relationship, very strong requirement. And if you're going to fail delivering equality, it's probably in this property. The next is, what is an order relation? The standard talks about a strict weak order. What it means by strict is less than. Non-strict means less than or equal to. But the standard only cares about strict, so that's what we're going to focus on. But before we get to what a strict weak ordering is, we need to know what a partial order is. And it's irreflexive, it's asymmetric, and it's transitive. So the first two requirements are different from an equivalent. They're the exact opposite, but it shares the property of being transitive. And if you're going to fail in delivering a partial order, it's typically in the transitive clause. So the strict weak order adds this strange thing. A less than B implies A less than C or C less than B. What this means is that you have a set of ordered partitions, right? So every element has a relationship with every other element unless it's in the same partition. Okay? So the best way to think of this is you start with some total order, and then you partition it and say, okay, all of these things that are sort of near each other in the total order become an equivalence class, and they'll be considered equivalent for our strict weak order. And then we get to the total order, which is what we typically think of when we see the operators less than, equal to, and greater than. We typically think we're going to get a total order. And that has an additional strong requirement that it be trichrotonomous. What that means is that for every two elements, you have exactly one of those three relationships, less than, equal to, or greater than. Your most likely failures in delivering what you need are in creating the ordered partitions or in creating the trichrotonomous property. So what comparison orders are needed? Probably the biggest one people worry about is what sort needs. And it says it needs a strict weak order. And there's various other algorithms in there that need something a bit stronger. or a bit weaker. But the one thing the standard doesn't say anything about is what you need for your domain of computation. What works best for your domain for an operator less than? It may not be what the standard requires. So standard doesn't know, and the standard makes some assumptions. So what can go wrong? Well, the thing you should be most worried about is your bank balance may suddenly disappear. You never know what might happen, because if you go wrong, you're often in undefined behavior territory, and then you have no idea what's going to happen. I am going to use some examples with floating point numbers. I'm going to use these examples for a couple of reasons. One is that it's a built-in type. It's kind of hard to ignore the problems in floating point because they're going to carry on. But the problems do apply to other types, and I'll get into that a little bit later. But the net result of this is that, contrary to what most people think, the standard does not support sorting floating point numbers in general. So passing general floating point numbers to STD sort is undefined behavior, and you may get an anchovy pizza within the hour. You just don't know. So how is sorting with NaN? Well, we're going to look at the standards requirement for a ordered partition. And if we compare 1 and 3, 1 less than 3, that's true. But NaN doesn't compare less than to either of those, so it doesn't meet that requirement. So let's put some 5 numbers into a sort. A couple of those are NaNs. We'll sort it, and with different partitions on the input, and we get wildly different results out of the sort. And what's happening here is that any NaN in the data tends to partition the sort into independent subsets, which are then sorted, right? And our partitions tend to be pretty small, so it looks pretty random. But if you do a binary search on something that's been sorted with a NaN in it, you're probably not going to get a large chunk of your data ever looked at. So this kind of behavior in sort is not only undefined, it's not very helpful. Okay, so how is sorting with sign 0? Remember, IEEE floating point has both a positive and a negative 0. This operator meets the, if you ignore NaN and assume that NaNs don't exist, then the operator equals for floating point does deliver a strict weak order. But it does not deliver substitutability, because 1 divided by negative 0 is negative infinity, and 1 divided by positive 0 is positive infinity. So it's not an equality. But that's okay, because sort doesn't require equality. But if we have our set of 5 numbers with some positive and negative zeros, we sort them, we'll get an order that's not consistent given the input. All of these are correct. The algorithm is delivering what it promises, because all of the elements in the partition are together. They're just not in a consistent or reliable order. It's correct, but it may not be what folks expect. But let's go a little bit further for memoization. So we've determined that operator equal does not provide substitutability, therefore it's not an equality. So if I do a memoization over 1 over x, and I give it minus 0, plus 0, and minus 0, what I should get out is minus infinity, plus infinity, and minus infinity. What I do get out is minus infinity, minus infinity, minus infinity. So we've got the wrong thing there. And if I reorder the input, I might get plus infinity, plus infinity, plus infinity. What's happening here is because -0 and +0 compare equal, the first one into that bucket defines the result for everything in its partition. That's probably not what we want if we're doing memoization. 1 over x is not the only function that has this behavior. There are several trig functions that have this behavior and so forth. So how is memoization with nan? So the sign zeros were our easy case. Let's go to nan. Nan equals nan is false in IEEE floating point. So operator equal is not reflexive, which means it's not even equivalence. It's so far off the map, you don't even know what it is. So let's take 4 numbers, run them into our memoization algorithm with 1 over x, and we should expect nan, nan, plus infinity, and nan. Okay, what we get out is nan, nan, plus infinity, and nan. Really? We have an algorithm that's so totally broken we don't know what it means, and we get the right results. Okay, so what's really happening here is that nans never compare equal to each other. So the hash table does a lookup. It will never match against the prior nan, so it allocates a new bucket, fills it in, does the computation, dutifully records the answer, and never looks at that answer again. Every nan you put in the stream allocates a new bucket and is subsequently ignored. So you have found a rather excellent way to waste programmer time, CPU time, and memory. Okay? So we don't want to do that. So how do we make things right? The first thing we have to remember is that in IEEE double, there's not a nan, there are 8 quadrillion of them. Okay, this is something most people don't worry about, but there you have it. There are some bits that in the nan that tell you where that nan came from. Implementations can use those, and IEEE arithmetic defines its operation such that it preserves those things. So every one of those nans is distinct and should show up in operation. So we memo nan number 1 plus 0 nan number 2. We should get nan 1 plus infinity nan 2. So with the default comparison, we're back to the same problem we had earlier where none of the buckets get reused. If we use a weak order, we somehow go in and decide that all nans are equivalent. What will end up happening is we'll fill the first bucket with its first element in the equivalent class and never get the others. So we only get the first one. When we impose a total order on the floating point numbers, we get the right output. So we get the right result once we apply the total order. The important point here is that for any value that might possibly be distinguished from another in any function on the type, we need to provide a total order that exposes those differences in values. Only then will our memoization be fully effective. So we've talked about floating point and how that can go wrong. And is this the only problem? Other primitive types like int are usually, but not necessarily, ordered. The standard allows a ones complement representation of int. Now, I've never actually worked on one of those machines. I doubt anybody in the room has done so, but the standard still allows it. Oh, you have? Okay. That's a rare case. Maybe you could just write it in page 362 of your documentation that doesn't work. But these problems get a little bit harder to shuffle under the rug when we move to user-defined types. So anytime you have a type with more than one field, that's almost inherently a multidimensional type. And there's usually not a good natural mapping of a multi-dimensional type onto a total order. You have to think about what you're doing there and make sure that you actually do get a proper mapping. And it's hard to do this because you're using some type that you got from some library, and you go look at the library documentation, and it dutifully gives you a less than operator, but it doesn't tell you what properties it meets. So you're going to have to go on trust. And most people never think about that. They assume a total order, but in fact, in many cases, it's not a total order. And we know that for floating point, it's not a total order. In fact, for floating point, we know it's not even a weak order. We don't necessarily want to require that people give a specific order because they wrote their less than operator for use in their application domain for the algorithms that are central to their type. Right? They didn't do it to make the standards job easy. They did it to make their job easy. So what is the real problem here? The real problem is that the standards utility algorithms use the operator less than by default. But operators may not meet those guarantees. And we should not have those guarantees imposed upon certain types. Okay? What we've got here is one operator trying to serve two masters. And that will probably not serve either well. What we need to do is separate out the comparisons we use for utility algorithms from the comparisons that we use for the application domain. Can it get worse? Actually, yes, it can. The standard helpfully provides some facilities for us to automatically generate operators. Okay? In fact, what it defines is the implementation on the left. It lists this in the standard. This is exactly what it does. But this fails when T is partially ordered. It doesn't give the right results. That is, it fails when you give it a floating point type. So what you should do is the alternate implementation where you do exactly what the operator name says. It's greater than or it's equal to. And then you get expected behavior. And this gives you the same results even as the floating point operators do when you apply it to float. So getting clever in your definition of these operators is counterproductive. So the important thing is, what can you do about this problem now? So I've outlined a couple of bugs. You can go and hunt for those bugs now that you know about them. Explicitly check your data for nans. That's one way to avoid a lot of problems with sorts. You can go and look at your code and prove that the operators you have the properties you want. And if they're not weakly ordered or totally ordered, you probably need to say that in the documentation. But you can write new code to avoid the problems. And that's mostly what I'm going to talk about now. So what the advice I'm going to give you is to not use the operators, with the user-defined operators with utility algorithms. Because you just can't trust them. You have no idea what's going on. Which implies that you can't use std-less with the standard algorithms, because that typically just picks up operator-less, right? Which just shuffles the problem through one more layer of abstraction. So what do I suggest you do? I suggest you write well-defined comparators that match the properties that I've discussed earlier, and then pass them explicitly to the utility algorithms. They all have an additional comparator argument. People usually default it, but you can pass it explicitly. Hello? Okay, it was way behind on me. So what are the Boolean comparison functions we write? Well, we had 3 levels of relationship for order, and those actually imply 2 levels of equivalence relation, and then a pairing to partial orders. So we have a partial order, a weak order, and a total order, and with the less operator. And then we have the equivalent where it's unordered in partial. That's got an equivalence in weak, and it's equal in total order. Okay, so we just write these functions and carry on. If you use these names, then we'll build a community where everybody expects the same thing. But I have to caution you that these names are not in the standard, and the standards committee is known for renaming things. So don't get too surprised if the names happen to change in the future. The next thing you need to do is be consistent. So don't develop these comparators in isolation. You have a whole set of issues, these interrelate. The first thing is you want to make sure that the equivalence class operations are written in terms of less than, or the less comparators, or they're effectively equivalent to that. You want to be consistent across levels. So if there is an order imposed by a weak order, and somebody then goes to use the stronger total order, they're going to expect it to be consistent. So you want to make these consistent as well. You want to be consistent with the operators that you provide for that very same reason. People are going to use it one way with the operators. They're going to expect these comparisons to at least be consistent, so do that. And finally, if there's a standard out there that applies, you want to be consistent with that. For floating point, there is a standard. It's a total order function. So fine advice, but how do we go about doing that? First, operator less than already implements a partial less, so we can just use that in our definition of partial less. We can write partial unordered with partial less, as I showed earlier. Now we have to write total less respecting the IEEE total order. Then we can write total equal with that. And now we get to the middle case, which is often the one that seems to be a little bit more work. We write weak less and weak equivalence with weak less. Let's go into that a little more detail. The IEEE total order puts all of its values in this order, starting with positive quiet nans to positive signaling nans, all the way down to negative quiet nans. Every bit pattern is distinct because there exists some operation that will give different results on different bit patterns. Okay? Now, sadly, the order up here is not the same as any integer type you're likely to use. So you can't just cast to int and compare. I wish it were so. Now when we move to weak order, remember a weak order is a total order among partitions. So what we want to do is take the total order that we have for a floating point and partition it up. The partition that makes most sense is to make all positive nans equivalent. Then you have positive infinity, each of the positive reals. Make the 2 zeros equivalent. The negative reals, the negative infinity, and all negative nans are equivalent. So this gives you about as close to the operators as you can rationally get. Now, both the strong order and the weak order have their uses. It's perfectly fine to have both of them in there. Then you need to check your relationship with the operators to see if you're consistent. I've done this. The total, equal, weak equivalence, partial ordered, and descending strength. And then we get to operator equal, equal, which is even weaker than that. Okay? On the left side, total is stronger, weak, and then partial less and operator less than have the same strength. They're essentially the same. So we have a good consistency there. When you move into implementation, though, what you want to do is make sure that you take care of the common cases first, right? Nands and negative zeros are uncommon in most code. It'll be a small number of things that you see, small percentage of values that you'll see those. So we don't want them to slow down the computation. So we can test regular doubles. If it's less than, we know it's true. If it's greater than or equal, we know that weak less is false. And then we can go into the other cases, which takes a bit more time. Now, in case you're worried about me waving my hands too much, I'm providing my code for all of these examples and the implementations to the conference for them to make available for anybody that wants them. But I do want to caution you that if you compile on the IA32 architecture, the ABI basically turns signaling NANDs into quiet NANDs at the first opportunity. So it's hard to do any testing on signaling NANDs. Okay, we've done floating point. Now let's go into another example. And what I'm going to do is look at zip codes, and in particular their relationship with zip plus 4 codes. For those of you that are unfamiliar with US postal codes, zip plus 4 is an optional extension to the regular zip postal codes. The optional part represents a challenge. What we want to do is figure out how to sort zip codes when they might have 5 digits or they might have 9 digits. One way to do this is just to consider them all strings and do a lexical sort. This provides a total order, so it's good for sorting, but the problem is it sorts 1, 2, 3, 4, 5, 6, 7, 8, 9 as very different from 1, 2, 3, 4, 5. And if we're trying to look to see if it's the same address written 2 different ways, then we've separated those in the sort and we're not going to match up. So you might think, okay, well, we'll just make a 9-digit zip equivalent to its 5-digit zip so that they'll compare equal. Okay? The problem is that if you look at the relationships, you can prove that they don't meet the ordered partition requirement. So it's not a weak order, and it's not satisfactory to the sort algorithm. So we don't want to do that. But what else can we do? Well, what we can do is make every 9-digit zip equivalent to the same 5-digit zip, right? So that you basically ignore those last 4 digits and only look at the first 5. Okay? That gives us a weak total order, or sorry, a weak order, because we've partitioned the total order into coherent chunks. This is helpful when you're doing a sort to look for addresses that are the same, and it's useful in the context where you've got other address information that's strengthening the comparison based on the other fields. Okay, the essential point of this example is that both a weak order and a strong order have reasonable use cases, and we want to enable both. But before you go out and write your own address application, actually the better approach to looking for addresses that are the same is to use various services that will normalize addresses. The post office will do that for you. So I don't want to give people the impression they should run away and code up this stuff right away. So that's another example, but remember our primary problem was composite types, where we have more than one field. So let's look at some comparison algorithms and see where we get. Sort of the first one is if every field says less, well then obviously the composite type compares less. This works, but it will only ever produce a partial order. You can demonstrate that it's not transitive, and so it's only a partial order. The next algorithm is, okay, I only require that one field say it's less. And as long as none of the others say it's greater, it's consistent, nobody's objecting, and so I'll call that less. Well, you can pretty much prove that that thing is only a partial order. But more importantly, you can prove that it isn't an order at all if any field is partially ordered. So for this algorithm, every field has to have a weak order for it to succeed at all. Okay? So both of these algorithms produce a partial order. One might give you better results in certain applications than another, but they're both still partial orders. The third algorithm is lexicographical. This fails when any field is partially ordered. You can demonstrate that it doesn't give you a weak order. So it's useless in sort. Otherwise, it produces the same order as the weakest field. So if you have any field in your type that has a weak order, the use of the lexicographical algorithm will only deliver you a weak order. Okay? More importantly, when you use the lexicographical order, the field order defines the comparison order. So you have to think very carefully about which fields you want to compare first, because that's your major key, right? The next key is your second key, and so on down the line. So you have to decide which parts of your field are most important to compare. And there's another technique in here that I hesitate to mention, so I didn't put on the slide, and that is to just use memcompare over the type. As it turns out that this will dutifully compare your gaps between fields, and it will dutifully compare your pointers to string rather than the strings themselves, and all of that. So please don't use memcompare. All right. So now you have an approach of what you can do, but it's not exactly nice. So what can the standard do? Well, the first job the standard has to do is maintain backwards compatibility. We simply cannot afford to break trillions of lines of code. But what we can do is enable migration to separating out comparison on the application domain with operators and comparison for the utilities with comparators. We can provide order and equivalence functions for all the standard types. This gets a little bit tricky when the standard type is a template and it takes a user-defined type. So it will take a little while to migrate the code, because if it's a template type, it needs one of those less operators to have been implemented on the types passed in so that it can reconstruct it for the following one out. So if you do a basic string of your favorite character type, it won't know what the ordering should be. There is more. So we have a problem in the standard library. If I give you the first code comparing a string, we're going to go look at every character in the string twice. Okay? The string provides an operator that gives us the result in one go. And then we only have to test an int to see which way to go in our branches. Okay? So we know the second way is more efficient. Now, let's repeat that process for every field at every layer of abstraction. So we go down the left side of our abstraction all the way down. Oh, it's not less than. Let's go back up the layers of abstraction. Now, is it greater than? Let's go back down the layer of abstraction. So we're revisiting the leaf nodes many, many times. And simplifying the order analysis, we basically double the base of the exponent. And even I can figure out that 2 squared is much smaller than 4 squared. Now, the problem we have is that the standard library has no way to do the efficient thing because they use operator less. They're stuck with migrating up and down the abstraction tree. So what do? We make sure that our standard algorithms can accept trinary comparators as returned by like s.compare. Okay. But the next question is this a weak comparator or a strong comparator? The actual answer is it needs to be all 3 of the comparators that we've had. This way, when an algorithm like sort says, I need a strict weak ordering, it can say, I expect a function returning type weak ordering. And it knows what to do with that. Okay? If you're doing memoization, you would say, I need a function returning a total ordering. And then it will pick up the appropriate function, carry on, and act appropriately. So in addition to getting the trinary comparators, we also get a trinary comparator that's very explicit about the relationships we require to make the algorithm work. So rather than a small sentence buried deep within the language standard, we can actually get a compiler error if we do something wrong. So the next question is, can we make coding easier? Well, we can with some defaults. The first thing we can do is think about providing an explicit default for partial order. The problem here is that while unanimous always works, uncontended is sometimes better. And do we want to make the default conditional on whether or not there's a weak order? Or do we want to just say, you're on your own if you want to construct a partial order? We could probably get away with that because I don't see a lot of people being concerned about partial orders. We can provide an explicit default for weak order, and that's pretty straightforward because only the lexicographical algorithm works. And it needs weakly ordered fields. So you could construct it automatically by calling the same function on its fields. And we can do the same for total order. It requires totally ordered fields. And to avoid having to implement the same thing twice, we can apply implicit defaults so that if you provide a total order, we can infer from that that you have a weak order because all total orders are also weak orders. With these kind of defaults, we can help with the production of the comparators. In many cases, though, if you want a sort order that's consistent with your operators, you may not want to use these defaults. If you're writing your own operators, you might want to do something more special. Given all that, what is the path forward for all of us to make things happen? Our first task is to separate responsibilities. Okay? You can solve the correctness problem yourself but your life would be much easier with standard help. So let's start off at the first sub-bullet, right? This is where you do all your Boolean comparators. So you can start solving the problem. The next thing that can happen is the standard can provide Boolean comparators to make your life easier. You don't have to rewrite those for the standard types. The next thing that can happen is the standard can provide trinary comparatives and algorithms overloaded for them, right? So that we will start shipping a new overload for std sort that takes a trinary comparator and does the right thing with it. That's a bit more work on this part of the library implementers. And then the next thing that can happen is the standard provides explicit defaults for comparators. And this will require a core language change. And now we can start, once we have all that in place, now we can start to push more strongly on this notion that the operators belong to the application domain and the comparators belong to the standards utility domain. And we can start pushing the algorithm defaults towards the trinary comparators and away from the use of operators. There is a proposal in the works, which is N4367, and any successors that will come out of that, in case you're interested in details. And given that, we move to questions. No questions.
So, in this, is the ordering fixed once and for all by the person writing the class, or can they, like in SQL with relational databases where they deal with ordering all the time? Essentially, you do select some things, and then you say order by whatever things you want to order by at that time. So, column 1, column 2, maybe one time you do that kind of query, but the next time you might do by column 3, column 4. And so here, is it all fixed once and for all at the very beginning? You have to decide this is how you're going to compare them?
I think for the question is, does the order have to be fixed at class development time, or can you defer it as happens in relational databases for tuple sorting and all of that? I suspect most people are going to want to fix it once and for all. That if you're doing variable field stuff, then you want something a little more general than this. So you would construct your own comparator, perhaps using lambdas or something like that, and pass that in. So you would still do the comparators, right? It's just that you might even dynamically construct a comparator to pass that into the sort. You wouldn't necessarily have sort by default pick up a comparator associated with the type. You'd pass whatever you want to do in explicitly.
You mentioned that the standard currently only cares about less than or equal. No, not in the same thing, either less than or if something is equal. Does it mean that when writing an application, if I can express everything in terms of less than instead of like greater than or equal, or would that have an impact in the speed of performance of the application?
Okay, so the question is, if I could define everything in terms of only less than and equal to, would that have an impact on the performance of the system?
Yeah.
And you can do that. It will be mostly as efficient, but there are a couple of cases where it might not be as efficient. The first case is that if you do greater than, that's simply a switch in the parameter order. Okay, so as long as you've got that in line and have a decent compiler, you'll have no performance. Okay, for less than or equal to, if you do it properly, you have an or between less than and equal to, and that could introduce overhead. So if you can implement less than or equal to directly, you might be able to avoid that overhead. Okay? Now, if you're lucky enough to have a totally ordered type, then you can do the trick of not less than to get greater than or equal. Okay, and that might save you a little bit. For the most part, the performance difference is not going to be huge there. But, you know, like if you're writing floating point comparison, you really want to be efficient because it's used everywhere. So it depends on your application. If you've got a big type, rarely used, probably doesn't matter. No more questions? All right then, thank you very much and have a good conference.